Okay, run the cells, run one by one cell. Okay, so that you can check which cell you need to correct. Okay. So after importing libraries and house train and house test, we then check the missing values, right? Kegel house price prediction. After loading the libraries and putting your working directory link, we have imported the train CSV and test CSV. Train 81 variables 1460, test 80 variables 1459. Then we identified the missing values, right? After identifying the missing values, we have added the dependent variable to the test data and fill the value with test. Then we have concatenated the data into house train and house test. Okay. So house train and house test, we have concatenated them into combined DF. All right. Then we split the data frame into object data frame and numeric data frame. So we have split the data. We have combined the data into combined DF. Then we have split the data into object columns and numeric columns. Once we have split the data into object columns and numeric columns, then we found the missing values in object columns, right? So object columns, once we find the missing values, we have identified those variables which have very high missing values. So we have imputed with the word missing, right? So then we check the frequencies of all other variables. And here you have to move the sale price column to numeric columns. First, move the numeric column after imputing the missing value as missing. After imputing the missing values as missing, the 5 missing values as missing, you have to move the sale price column from object columns to numeric columns. All right. This is the major correction which you have to do. You have to move the sale price from object columns to numeric columns. Then what we did was we dropped the sale price from object columns, and then we use the simple imputer to impute the object columns. We have used the simple imputer to impute the object columns. So before running the simple imputer, you should move the sale price from object columns to numeric columns. This is the first change which you guys have to do. You have to move the sale price from object columns to numeric columns. Then drop the sale price from object columns. Then drop the sale price from object columns. Then we will run the simple imputer. Simple imputer, using most frequent as a strategy, will impute the missing values. Right? After imputing the missing values, you check the missing values. If there are any missing, you find that there are no missing values. Similarly, in numeric columns, we will have the numeric columns. Then we separated the category columns from the numeric columns. Then we dropped those category columns from numeric columns. Then we printed the sheet. We have 43 object columns, 7 category columns, and 31 numeric columns. Then we filled the numeric columns lot frontage with median. That is the only column that has missing value. I think we have many missing values. So except the sale price, rest of the columns we have filled it with median. We have filled the missing values in numeric columns except the sale price with median. Then we have imputed the category columns using the same imputer which have used in object column. Then we did the label encoding of object columns. We have done the label encoding on category columns. Then we reset the index because indexes are becoming uneven. So we reset the index of all the 3 data frames. Then we concatenated the 3 data frames into one single data frame. Okay. Then we split the data into train and test data. Then we drop the sale price from your what you call test data, and then we split the train data into y and x. Then we converted the y, our independent variable, into floats. All right. So this is the process which we have done. So all of you correct the notebook till this point and tell me, all of you have corrected the notebook till this point? Yes? Huh? Corrected notebook till this point. Now, once you have corrected the notebook, now I want you to create histogram, box plot, and density curve for the dependent variable y. For the dependent variable y, create a histogram, box plot, and density curve. Anybody who has not sorted the workbook like this, please call me. I'll help you out with the sorting. The major changes: before running simple imputer on object data, you should move sale price from object columns to numeric columns. And then drop the sale price from object columns. That is the first change. And then you have to reset the indexes and all. Or you give the data reference to the notebook which I sent you and run all the cells. Import IO percentage series, give the reference to your data folder and then run all the cells. So what is your analysis of the variable, dependent variable? So what is the interpretation of your dependent variable? First, tell me the skewness, positive or negative skewness? Positive skewness. Positive kurtosis. Y dot plot time is equal to this. Y dot plot kind is equal to box, comma what is equal to false. So skewness is on to the left side, positive skewness, and then outliers on the maximum side. We have the outliers on the maximum side. Y dot plot and is equal to density. So narrow, tall peak, so positive kurtosis and positive skewness. So our dependent variable is positively skewed with positive kurtosis and outliers on the maximum side. That is the structure of our dependent variable. On such highly skewed data, the basic algorithm like multiple linear regression will not perform well. Will not perform well because it's a parametric algorithm. Remember, parametric algorithm means there are assumptions before the model being built. Multiple linear regression, binary logistic regression, we have assumptions, right? What are the assumptions? Linearity, multicollinearity, exogeneity, sample size related, residuals, normally distributed, post model, all these things are there, right? So parametric algorithms will have a lot of assumptions that need to be met before we run the model. Now, if you want to run a parametric algorithm on this data, multiple linear regression, is it possible? Because the dependent variable is not closer to normal distribution. Dependent variable is not closer to normal distribution. Dependent variable has outliers. Dependent variable is highly skewed and highly positive kurtosis. Yes, parametric models means there are assumptions that need to be met before running the models. Examples of parametric algorithms are multiple linear regression, binary logistic regression. Is this normally distributed? What is normal distribution? Bell curve. Does it look like a bell curve? Does it look like a bell curve? No, right? It's a clear-cut case. If it doesn't, see what is bell curve? Bell curve is a hypothetical situation. Remember that none of your data will be perfect bell curve. It's a hypothetical situation. Remember that part. Okay. In real-time data, we will never see a perfect normal distribution. See, bell curve, this is the right image you need to remember because you will get questions on bell curve. This is the important thing you need to understand. So, 68% of the variables will fall under, observations will fall under 1 sigma, 68.26. Okay, next what? Next threshold is what? 84% of the observations will fall under 2 sigma. 95% of the observations will fall under 3 sigma. Right? This is the normal distribution, Z scores and T scores. This is the diagram which you need to understand. So 99% of the values will fall under what? 3 sigma. 95% values will fall under what? 2 sigma. 2 sigma plus or minus. So when you say mean is equal to 0, 1, standard deviation is equal to 1, we are talking about 68.1% of data only. When you say mean 0, standard deviation 2, means we are talking about 95% of data. When you are saying mean 0 and standard deviation 3, we are talking about 99% of our data. So the bell curve, simply the size, what you call the design is not there. You have to understand the significance of the mean and standard deviation. Mean 0, sigma 1, you always talk about 68% values. You can see here, the critical values are also given here. 1.98 alpha, 2.58 alpha, 0.013 alpha. So here you can see here, so the Z scores are minus 40, minus 30, minus 10. Consider the Z scores and the T scores. So you need to understand this diagram very well. Okay. Now, we have found out the data is not normally distributed. Now, and we see that there is a lot of skewness. So if I want to correct it, what should I do? Logarithmic transformation, right? I will do logarithmic transformation of the dependent variable. If I want to correct the positive skewness, what is my primary strategy? Log values. Convert the actual values to log values and then see whether the curve move towards the center or not. That is the indication. The skewness in the curve should move to a certain extent to the middle. If it is going extremely towards the right and becoming negative skewness, then it's a problem. If it is going extremely right and becomes a negative skewness, it becomes a problem. So np.log y dot plot kind is equal to box, comma, what is equal to false. So the box plot will help us how the box move to the center. See, the box move to the center. In the normal box plot, the box is completely towards the left side. Now, when I converted the values from actual values, when I took the log values instead of actual values, the box moved to the center, and the outliers are split on the both ends. This is to some extent acceptable. This is to some extent acceptable. This will improve the multiple linear regressions performance. This will definitely improve the multiple linear regressions performance to certain extent. Okay. Now, even after doing this, if the multiple linear regression is not giving us the required R square and required lower RMSE, then we have to go to the next set of models, which is the tree-based model, decision tree model. Now, what is decision tree model? It's a non-parametric algorithm. That means there are no assumptions for tree-based models. Any tree-based model, be it a decision tree, which is a single tree model, be it a random forest, which is a multi-tree model, gradient boosting trees, which is a multi-tree model, any tree-based models, we consider them as non-parametric algorithms. There are no prior assumptions for these set of algorithms. So these algorithms work with outliers. They work with not normal distribution data. So we need to understand this part. The parametric algorithms suffer from assumptions. If assumptions are met, they are perfectly good algorithms. They perform better than advanced algorithms if the assumptions are met. And if the data range is between less than 5 lakh, not even 5 lakh, less than 1 lakh. If the data is less than 1 lakh, you hardly have 20-30 variables, linear regression will work well. But if the data is larger, linear regression will not give you the performance. Then we have to go to non-parametric algorithms. Non-parametric algorithms, tree-based models. Another example of non-parametric algorithm, KNN, k-nearest neighbors. Apart from regression models, what are the examples of parametric algorithm? Linear discriminant analysis is a parametric algorithm. In common interview question. Generally, what is the examples of parametric? We all say multiple linear and binary logistic. And if you want to go beyond that, we have linear discriminant analysis, lasso, ridge, and elastic net regressions. These are penalized regressions. These are also parametric algorithms. Okay, so you need to understand the dependent variable must be checked for meeting of assumptions before running multiple linear regression. That is the first part. Okay, now the second thing what we need to understand is the multicollinearity problem. We also have this multicollinearity problem, right? In linear regression, multicollinearity is also an issue. Generally, we look at multicollinearity after running the model, and if we get R square of above 95%, then we go back and check back your multicollinearity. That is one method of doing it. Second method is do beforehand. Identify multicollinearity and then build regression models. You can do both ways. You can build a model and then the model is not giving you high overfitting. Then there is no multicollinearity in your data. If multicollinearity is there, your adjusted R square will be greater than 95, or your R square should be greater than 0.95, or it can be 1. Then you go back and check, do the correlation analysis only on numeric variables. Correlation analysis must be done only on numeric variables. It cannot be done on dummy encoded or label encoded variables. Remember that. It has to, correlation is a descriptive statistic method. Remember descriptive statistics? It's a bivariate statistic, right? And descriptive statistics will be run only on numeric data. For non-numeric categorical data, we have frequency theories. That's a different analysis. So when you are running multiple correlation analysis, you should choose only numeric variables. You cannot choose dummy encoded, label encoded, categorical or object variables. Because now if you look at your object variables, they are also numbers, right? Post dummy, all your object variables will become 0 to n levels. They are all numbers. They will work. Regression will work and it will give. But will that output will make a sense? it doesn't make a sense. You should do correlation analysis only on numeric data, not on categorical data, not on object data. Categorical data, object data, if you want to find relationship, what is the test available? Which hypothesis test? Both categorical. Chi-square test of independence. This is again an interview question. You can check the relationship between two numeric variables using covariance and correlation. How will you check the association or relationship between two non-numeric categorical variables? Using chi-square test of independence. Null hypothesis is no association or relationship between both variables. Alternative, association or relationship between both variables. We need to regulate the t-test is mean comparisons. They are different tests. I'm talking about relationships here. Relationships, numerical relationship is covariance and correlation. Categorical variables relationship is chi-square test of independence. Okay. Now, on this data, we will build a linear regression model on our original y. We will also build a linear regression model on logarithmic y to check how the R square is changing. Okay. So, from sklearn dot linear underscore model, import linear regression. Reg is equal to linear regression brackets reg model is equal to reg dot peg x comma y. Reg model, why I'm using toggle here? It is going into toggle. Reg model dot score x comma y. Now, is it overfitting? No, it's not overfitting. So that means there is no multicollinearity in our data. You can check the correlation also. You will not see any multicollinearity in your data. Okay, so we got 85. This is what R square. This is your R square, which should be between, what is the range for R square? 0.60 to 0.95. Below 0.60, underfitting. Above 0.95, overfitting. First is multicollinearity. If it is overfitting, first thing is you should do correlation analysis and identify these multicollinear variables. Choose one among them. If you don't see multicollinearity and still it is overfitting, then you have to do feature selection methods. You have to identify certain variables and remove them from your model. Or you have to increase the data size. We studied that how to. We didn't study them. We'll study them later. We'll have a session on how to deal with bias, variance, prediction error, overfitting, underfitting. We'll study the techniques how to correct them as we go along with the course. Okay, all of you got the regression model. Now, in regression model, here we get regression model dot intercept. We'll get the intercept as 2,48,745. Print list zip x dot columns comma reg model dot coefficients. These are the coefficients of each variable. So we will import the regression model, then build the model, and then print the coefficients. And these model coefficients are used. Coefficients are used to build the regression equation. This is used to build the regression equation. The regression equation is built from these coefficients. intercept and coefficients. Remember, I showed you in Excel sheet how it is built. Same process is done here. NP.ext. Now we are not in it, because we used y only. We have used y here only directly. So now what the competition is regarding the test prediction, right? Reg test predict is equal to reg model dot predict house test df. So we got an error. So house test df, we didn't drop the ID column. House test df, just let me check the columns once. ID column is there. You have to drop ID column, right? Which we dropped from our train data. So house test df is equal to house test df dot drop single quotes ID comma axis is equal to 1. We have dropped the ID column from test. Now we will predict on our test data. We got the predicted values. Reg test predict. These are the predicted values for our test data. Remember, test data did not have a dependent variable. We have predicted them using our train data model. These are the predicted values for our test data. Now, to check this score, pd.data frame reg test predict dot to underscore csv reg dot csv. You will write the predicted values to the CSV file. You can copy paste them into sample submission file under the sale price, and you can upload it into the competition site. And you will check your score. So here we are writing the predictions. Test predictions to CSV. You're writing the text predictions to CSV file. You can open the CSV file, copy paste the values into a sample submission file, and you can upload it into the competition site to check the accuracy. So you have the sample submission file, right? This is the reg file and the sample submission. This is my reg file, which I have written into the sample. So I'll copy the values from here. Control Shift down, Control C, minimize it. Go back to the sample submission file. Under sale price, Control V. Do not touch the IDs. Do not touch the sale price. Below it, you have to paste Control S. Sample submission is updated. Just submit, na? You will get an idea what exactly is happening. Submit predictions. I will upload the sample submission file. Hackathon. Right, make submission. See, your submission score 0.35665. Of course, my best submission is 0.24297, but for this, I got 0.35. For the regression submission, I got the value as 0.35665. Right? What happened? You will also get the same score. That is a decimal change. Huh? There's a decimal change. So we don't look at that part. This is 0.356, right? That is the primary. We'll do that. Don't worry. We'll do that. All right. All of you got it? Now, let us understand the effect of logarithmic transformation. Impact of logarithmic transformation. So, reg model 2 is equal to reg dot fit x comma np dot log of I. X comma reg model 2. Reg model 2 is equal to reg dot fit x comma np dot log y. Reg model 2 dot score x comma np dot log of y. See, marginal improvement in R square 88.78. Your R square has marginally improved to 88.78. Okay. Reg log predict is equal to reg model 2 dot predict house test df. House test df. Now, reg log predict will get the values. Now, these are what? Log values. These are log values. The prediction will be log values. The prediction will be log values. You can see, right? Now, if you want the actual values, all we have to do is np.exp reg log predict. You will get the actual values. Reg model 2 is equal to, we already have defined the linear regression as reg. So we don't need to do it again. We are using reg.fit x comma np.log of y. Then we score the model. The model performance has improved from 85% to 89%. There is a big improvement of 4% is a good improvement. It improved. And we got the predicted values as this np.exp of the log values. We got the predicted values. pd.dataframe np.exp of reg log predict .2_CSV reg log .csv reg log .csv. I am writing the file as this. Now upload this logarithm value file into the competition and see how the score improves. So 0.35 was our earlier score based on linear regression. In the competition side, the linear regression gave us a score of 0.356. It is given there, no? Submissions will be evaluated based on what? You can go to the submission place. The overview. Leaderboard. Or rules, sorry, rules. So rules is leaderboard. What is this leaderboard? It went up to 0.14. No, that's a good improvement, right? So you guys also submitted desktop hackathon house price prediction reg.csv sample submission.csv. So this is the sample submission file. This is the reglog file, right? Control C. And in sample submission, Control V and Control S. Save the, close all the files, no need to keep them open. Submit predictions. Sample submission.csv. Reg log. Make submission. Jump to your position in leaderboard. See? My entry is now 1,991. It was earlier somewhere long back at 3,000 rank because of doing the logarithmic transformation. our best entry is now 0.14. The simple transformation of values into logarithmic is now giving us 0.1417. Where is 0.35? Where is 0.14? It's a very, very drastic improvement. Parametric algorithms have this problem. A minor adjustment in a parametric algorithm will have a drastic effect on the model performance. I request all of you to submit. Okay. That would be also if you download it, there is the data. Go to cables.com. Combinations. Search combination. House prices. House space. Prices. That's all. Now, joint combination first. Now go to the scroll down. They keep on playing. Submission. Now create a folder. Here you want to and then connect the folder. Where are you to do this? Yeah. What's wrong with it? It's learning process, right? GitHub profile also no function. You have to give a real name, and you have to be named your GitHub profile, right? And the link should be given to your resumes for them to check what you have done and not. And you have to do analysis, diagram, and all it will work. Go to the folder, right click on the right click on the folder, proper license.
Data scientist, data
Yeah, so we have the same price. No, we have done this first. Now, wait. When star is running, means it is running. 8 will become the number. Until then, you should not do it. Okay? Star means it is still running. Wait a minute. When the star becomes number, then you can do. Because this is the first step, now it is establishing parts for the now it can not stop it. Like that, we just go through one by one cell and then understand the notebook. So logarithmic transformation has drastically improved the score. So you write here why you did logarithmic transformation. When you are writing the analysis, because of positive skewness, to correct the skewness, we have applied logarithmic transformation. See, kurtosis is not corrected by this, only the skewness will be corrected.
Is there any scaling method?
No, kurtosis we can't do anything. Kurtosis will depend on the number of positive and negative values. That we can't do anything. Possibly, you got the prediction earlier also, right? But it is not the accurate one. Like, see how much it gave. The error was 0.35. Right? Now it became to 0.14. So prediction will come. Whether it is there, how close it to the actual prediction depends on the right methodology. So prediction will come. Software will give you the answer, but whether the answer is right or not, you have to decide, right?
So maximum error we have to measure.
Minimize the error.
No, like
you always minimize the cost, maximize the profit.
No, maximum error we have to like is that a comparison metric? Like it
RMSE, na good mixed error. You compare the model with RMSE. Of which model?
These values.
The model which has the least RMSE is the best fit model. I told that diagnostic is RMSE. In classification, it is accuracy, confusing matrix and accuracy. What? Right? All right. Now let us do the regression without max depth. Okay. Decision tree regressor. From sklearn.tree, import decision tree regressor. Tree is equal to decision tree regressor. Tree is equal to x comma y. Tree model dot score, we got 100%, which is a overfitting scenario. Which is a overfitting scenario. Sorry. Right. Now,
when we are cross-validating the score, like every time it shows a different number.
yes, sample subsets of data will be randomly selected. Na? There is a random seed.
Showing a lot of variations. Like
That is the overfitting problem. That's why we call it as the overfitting problem. Train model train model R square and your CV R square will be drastically different. That is another example of cross validation. Another feature of cross validation. Sorry, overfitting. One way to identify overfitting is R square above 0.95. Second way of identifying overfitting is when you rerun the model again, your R square will drastically decrease. That is the overfitting. Second method of identifying the overfitting. Now here we have seen that model is overfitting. Right? Let us predict. Tree predict is equal to tree model dot predict house test df. Tree predict. Got a predicted values.
these are just two different different models.
So which one?
Like if we have obviously we'll have different models.
There is no random seed in basic decision tree model. You will also get the same values, 1,22,000. Remove the max depth. If you remove the max depth, rule-based prediction, you will get the same value repeated again. Because this is a rule-based prediction system. Huh? Same values you got? Okay. Now, PD dot data frame tree predict dot to underscore CSV tree dot CSV tree dot CSV. Okay, so we have written the values into tree dot CSV. Sample submission file, and then the tree dot CSV file. Here you will not get in decision tree, you will not get decimal values. So if I submit the prediction,
We both got the same values. But they are different from your values.
Not much of a difference. Let's see. Make submission. So jump your leaderboard prediction. See, my submission scored 0.20611. Compared to the this thing, it is performing well. But it is showing it as 0.20611. 0.20611 is what it is showing. Where is this thing? (0.20611). Now, here also we will do the same, understand the impact of NP dot log of y. NP dot log of y. Okay, we got these values. NP dot ext dot csv. So 3.csv, we got new values. Control C. Go to the sample submission file. Control S. Overwrite the values. Okay. 3.csv. Then I'll go back to my submit prediction. Sample submission, open. 3 and log. Make submission. Shit. I think sample submission is a problem. Oh, 0.20971. Not much of a difference because this is a non-parametric algorithm, right? Here, logarithmic value is not giving us any advantage because it's a non-parametric algorithm. 0.20971. It didn't increase or decrease, it is staying in that same level. But for decision tree, the max depth is a good, interesting argument. Oh, sorry. Infinity came. Sorry, I didn't correct the EXP pattern. 0.20336. Max depth I took 12. For you, how much you took? 0.20. 0.20. Max depth how much? Normally we got the same thing. If I do max depth is 6, that depends on the trial and error only. అదే చూడాలి కదా. That's what we are looking at now. With max depth 6 also no difference. It is going between 0.20 to 0.21 only. So for max depth also it is not increasing much. Even if you control the depth, our decision tree is giving us 0.20. Huh? That's what. It will increase. But this is not a parametric, no? Non-parametric algorithm. So my intention is for you guys to understand what is parametric and what is non-parametric. How important are the assumptions? That is the understanding we need to have. So whatever may be the depth of the tree, 0.20 is what we are getting. 0.20 is what we are getting. Whatever depth of the tree I am giving, even if it is 12 or 6 or 8, which is between 0.2033 to 0.2099. So it is in that range, it is moving. So there is no point in increasing or decreasing the depth. Okay, where is undo? Still overfitting, huh? The strain accuracy is 90%, test accuracy, cross-validated accuracy is falling. Depends on your data. So cross validation repeatedly tests the model. By default is 5 times with randomly selected subsets of the data set. It randomly selects the subsets of the data set and then test the model. You can see here the cross val score of decision tree is on train data we are getting 90%, but on test data we are getting 71%. On an average, if you take the average also, it will be somewhere around 70%, right? Cross-val score, reg model or reg, comma, x, comma, np dot log of y. So you can see here, we got overall accuracy, how much? 88.89 on regression. So this is regression. What was our original train data? I think 0.88 something, no? Just 88789. Our original is 0.88789. Now, cross validation is also, if you take the average, it will be somewhere around 86 or 80. That means linear regression does not suffer from overfitting problem. Only decision tree will suffer from overfitting problem. But if you take the average of these, see 89, 85, 88, 88 and 172, even if you take the whole thing, it will be about 85%. 84 or 85% you will get the average R square, which is close to your 88% R square. So decision tree is prone to overfitting. Decision tree is prone to overfitting. Okay, all of you got this? Now, like I told you, decision tree only disadvantage is over fitting. And to reduce overfitting, we can do these things. First one is apply pruning. Pruning means cutting the sub branches of tree based on complexity parameter. We all cut trees, right? To make the tree growth properly, generally we cut the trees, right? We'll take the big scissor and then we'll cut the trees. Same type of pruning can be applied. Pruning can be applied on decision tree model. We have pruning methods which are applied. So first type methodology is you apply pruning. There is a pruning methodology which is applied. I'll tell you how to apply pruning in the tree. If you don't want to apply pruning on the decision tree, you have to control max underscore depth. Now, typically max underscore depth will be between 1 to 32. So max depth should be reduced, because if you increase the depth, more branches will come, which will lead to more overfitting. So we should reduce the max depth. We should not increase the max depth. We should consciously reduce the max depth. Because if you increase the max depth, new branches will be added, which will lead to more overfitting. So the second, if you don't want to apply pruning, you can control the tree growth by applying the max depth. Next. Yeah, it will. Always reduce the depth. It is all trial and error. There is no fixed formula. You have to do it with trial and error. It will change. The tree growth will alter, right? Min underscore sample underscore split. Once you go to advanced models, we have to look at this min underscore sample underscore split. That is minimum number of samples required, to split an internal node. This is a very common question these days in interviews and in MCQs also. I'm seeing, how do you reduce overfitting decision? In the last 3 MCQ tests, this is a question, and interviews also, CapGMI, they asked this question. So 3 students. When the student said max depth, they asked what other methods you can apply. So for them, I discussed pruning, but they didn't remember pruning, but they said max depth only we learned. So I told them it's max depth and pruning, but beyond max depth and pruning, you can also control samples per split. So this has to be between 0% to 100%. Now, 100% will lead to underfitting. 0% will lead to overfitting. So you have to find a value within this range. You have to find a value between 0 to 100% to reduce the overfitting or underfitting. So generally min sample underscore split is 0.5. I think in SQL and Python, it is 0.5. Let's check the code once, then you'll understand. This is one method of controlling the minimum sample per split. Is another method to control the overfitting. Min samples per leaf. Min underscore samples underscore leaf. What is a leaf? Terminal node, or last node is the leaf. Terminal node. So here also minimum number of samples. Required to be in leaf. Minimum samples required to be in leaf. So you can use any of these methods. One is this complexity param. You can use any of these methods. 2, 3, 4. Now, if you don't want to use this method, any of these methods, random forest algorithm which is developed exclusively to overcome overfitting in decision tree must be used. If you don't want to tinker with any of the parameters, but still you want to reduce the overfitting, you have to go to the next set of algorithm called random forest. The reason why random forest was developed by the statisticians is to overcome the overfitting problem in the decision tree. To overcome the decision tree overfitting, the statisticians developed this algorithm called random forest. So how many number of samples required to be in leaf? Ultimately, percentage of samples will go into leaf, right? Observations will keep on getting classified in the leaf. If a leaf has 40% observation, that means that leaf will be closed. It has to look for another set of leaf for putting the observations. Now in Python sklearn, we have all these arguments. In R also we have this, but in sklearn decision tree classifier, we have all these things. See here, mean samples per split is equal to 2, mean samples per leaf is equal to 1. You can see the arguments clearly given here, and you can see here, here. If in, then consider as the minimum number. If float is a fraction and are the minimum numbers. So if you give it as a float, decimal number, it will take it as percentage. If you give it as integer, it will take as the minimum number. Then same thing here. The minimum number of samples required to be at a leaf node. A split point at any depth will only be considered the leaves at the least. So that means if one leaf has reached its maximum level of samples, then the next leaf will be automatically created. And even if the observations are pushing into that leaf, they will be pushed into the next leaf. So you can specify the percentage of samples to be observations. When I say samples, I am talking about the observations.
40% are there in one leaf.
Then it will definitely go into the, if you fix a parameter, it will automatically go into the next leaf or next terminal node. Okay. Friends, sharing or not? Sharing, right? It's a very important question for interviews as well as your written test. Make sure you understand these methods. Got it? All right. Shall we go to the next set of algorithm? Now, multiple linear regression to tree-based model. Within tree-based model, we look at the single tree model. Single tree model is the decision tree. The output is a tree. Oh, I have not shown you the tree, right? SQLN export graph list is there now. 1 second. Okay, now from sklearn or tree import plot underscore tree. So tree 2 is equal to, I'm just reducing the max depth so that you can see the tree. Actually, otherwise the last tree it will not print properly. Actually, this is a theoretical description. ELT dot figure its size is equal to 30 comma. Let us see. Now we got the biggest tree. Now you can see the tree, all of you. So here. Yeah. I increase the plot size to 30 by 15. Then you can see the theoretical tree is this. The first step is having x square in bracket 72. 1 second. We have to add the plot tree, comma, not colors. features underscore names is equal to x dot columns. See? Now you can see the nature. First variable set is overall quality less than equal to 6.5. All right, all of you could see the tree. This is the theoretical explanation of the tree. And then you can see the tree diagram. In R, we get a very good clean diagram with all the rules and all. Here, I think we don't get the rules, we are getting only the tree. So we have this plot tree function to plot the decision tree. So the plot tree function, see max depth you can give, feature names, label all, field is equal to true. Field is equal to true will give colors. You see the colors. Field is equal to true. Here, given explanation. Squared error. It is not using Genie, it is using squared error. In Python, it uses squared error. Left side is yes, right side is no. By default, left side is yes, right side is no. Yes or no? Left side is yes, right side is no. All right. Now, it's split. It's there now. It's clearly given here. The first split is overall quality less than 6.5. Left side is yes, right side is no. Then next variable is overall quality less than 5.5 onto the left side. And on the right side, again, great living area. So you can see here, the first split, see here. Yes or no. Yes is this, no is this. Again, this split into greater living area 13785, ground living area 1941, left and right. And finally split it into here. But actually the trees are larger tree, but they are looking at only 3 levels.
There is one side.
R is a different diagram. R is a different diagram. Here we don't have leaves here because it's a partial tree. It's a large tree. Here we are not putting the full tree. We are just plotting the 3 depth tree only. There is no leaves here.
Also in the last step, sir, why did the parameter change? Like general living area for 3 cells and on the last cell for the second.
This one. This is a separate tree. This is a separate tree. So this is a, that means there is the other side of it is a terminal node. This is a separate branch. See, here you will not be able to understand. In R, I will show you the plot and also the rules. Here we don't get both of them. So that's why here it is not there. When we do the exam, same example in R, I will show you how the tree looks like and how we can look at the variables and how we look at the what we call the branches and all those things. R gives you the detailed outline. And the rules also, how the rules are formed for prediction. Here we don't get the rules. That's another problem.
These rules are
If the same thing, if overall quality is less than 0.6.5 yes or no, yes, then greater ground living area is greater than 13.59 yes or no, like that it will create rules. So the rule creation is very clearly in R, not in this place. Here we are not in the full tree here. We are taking only the partial tree. Now, continuing with tree-based models, multi-tree models. In decision tree, only one tree is built. In decision tree, only one tree is built. Whereas in multi-tree models, also called as ensemble tree method, multiple trees are built. Multi-tree models, where the output will be number of trees you would specify, that many trees will be built and the aggregation of the output will be done. Ensemble methods, one of the most prominent ensemble method is bagging, or also called as bootstrap aggregating. Bagging or bootstrap aggregating. And the popular algorithm is random forest. The popular algorithm in multi-tree models, ensemble methods. Within ensemble methods, one of the popular method is bagging, also called as bootstrap aggregating. Bootstrap aggregating, a popular algorithm is random forest. Random refers to sampling method. You all remember random sampling, unbiased sampling, randomly taking, random sampling. And forest refers to multiple trees. Multiple trees. The word random forest, random represents the sampling method it uses, and forest refers to the multiple trees it builds. That's why the algorithm is called random forest. Now, in this algorithm, the first step is, step 1 is specify the number of trees to be built. The number of decision trees to be built. Not simple trees. These are simple, like your exact decision trees, how you are building in the single tree. Exactly, same trees will be built. Let us say n underscore estimators. We use the word n underscore estimators referring to the number of trees. So here we are saying to build 1000 decision trees. So step 1, you need to specify the number of decision trees to be built. Here I am giving it as 1000. Step 2, 1000 samples of data will be created using random sampling method, and for each sample 65% of random 65% of observations randomly sampled and square root of number of variables, square root of number of variables per sample. So it will not take all the variables in the sample. 1000 samples it will create. How it will create? 65% of the randomly selected rows and square root of number of variables randomly selected. Suppose you have 25 variables. Square root of 25 is 5. So each sample will have 65% of randomly selected observations and 5 randomly selected variables. Random selection of rows and random selection of variables per sample. Now, this sampling process is the most critical process here. The sampling method, apart from being random, also uses bootstrapping or sample with, or data with replacement method. Data with replacement method. Data with replacement method means every time a sample is created, it takes this total sample into consideration. Typically, two things can happen. Once sample 1 is created, all the observations of sample 1 will no longer be considered, they will be thrown out. On the remaining things you can take. But it will not do like that. First, it will take sample 1 from the total data. Once sample 1 is created, all the observations are sent back to the total data again, and sample 2 is again created. Now, which means observations which appeared in sample 1 can also come in sample 2. That method we call it as data with replacement. Variables which came in sample 1 can also come in sample 2. Here, observations and variables will appear in multiple samples, thereby in multiple trees. So the logic here is, the more number of times the observation and variable appears in different trees with different combination of observation and variables, its probability of correct prediction will increase and the overfitting problem will automatically decrease. By doing this bootstrap sampling, the statisticians found out that the oversampling problem, which is the problem with single decision tree model, is eliminated. Bootstrap sampling or data with replacement means every time the sample is created, it takes into account the total sample for the new sample, which means observations and variables that appeared in previous samples will still appear in future samples. The more number of times the variable on the sample and the observations appear in different samples, the more likelihood or chances of it being correctly predicted will be higher. Wisdom of crowds. You know, wisdom of crowds, right? Committee-based decision making as or one person decision making. One person decision making, we can make extreme decisions. But if it is a committee, a 10-member committee is deciding, will you have that extreme decisions? We will not. Same logic is used here. By passing the observation and variables through multiple trees with a different combination of observations and variables, the overfitting problem will be eliminated, and also the chances of the probability of the observations being predicted correctly will also increase, or the RMSE will automatically decrease. So that is the importance of random, what you call random forest algorithm, the sampling. And until sampling is done, step 3 will not be done. It will not be initiated. Until it creates 1,000 samples of data, step 3 will not be initiated. If some problem occurs in terms of memory problems, memory size is not enough for 1,000 samples, the algorithm will throw error and will stop there. So the most critical part of this algorithm is the sampling. What the 1,000 samples must be created. Then only it will go to the next step. Okay, so step 3. Upon completion of 1,000 samples, decision trees are parallelly built that is one sample, one decision tree, and parallelization is possible as each sample is independent. Each sample is independent. You can simultaneously build multiple trees, parallelization, or parallel building of decision trees. Parallelization or parallel building of trees. One sample, one decision tree is built. And the splitting methods are all same. Splitting methods are Gini and entropy and information gain. Actual decision trees will be built. How the single tree is built, same process will be followed for every tree. Step 4, each tree will also predict and step 5, the aggregation of output, aggregation of predictions. If it is a classification problem, majority voting is implemented. And if it is a regression problem, averaging will be done. Majority of voting means the observation appeared in 200 trees. 120 trees predicted it as yes, 80 trees predicted it as no. The final prediction will be yes, majority voting. Similarly, it came in 150 decision trees in regression. It takes all the 150 predicted values, sums it and divides it by 150. We will get the average predicted value. So the final prediction is based on, if it is classification, majority voting. If it is regression, it is average. So this is the process of doing a random forest algorithm. Yes, please.
All these trees to predict or do we make the most accurate?
No. It's not tree selection. It is observations, prediction selections. All trees will be considered. Here, it is not the best tree. Here, the prediction of the observation based on the majority voting and average.
for everybody.
Every prediction. For every observation, every row, it will aggregate the output of all the trees in which it appeared, and then it will do the voting or average. Yes, 1,000 decision trees will be built. Yes, each tree will also predict for every observation. Yes. Once the sample is created, tree building is not difficult. No? The whole problem here is sampling. Once sampling is done, based on the number of cores on your CPU, it simultaneously builds 4 trees or 5 trees or 6 trees. Simultaneously, parallelly. Parallel building of trees will happen. So the tree building is very fast, and the prediction is also very fast. Aggregation is also very fast. The only problem is sampling. If the sampling is executed correctly, then parallelly it will single point of time, it might be building 6 trees or 7 trees based on your CPU power. And then accordingly it will predict for each tree simultaneously. Build, predict, it will do for trees, and all observations will be a comprehensive aggregation will be done of all the observations in different trees and outputs, and that will be your final prediction will be based on majority voting and average. So what you need here is computing power. The biggest disadvantage of random forest is computing power. It requires high power CPUs and GPUs for running the algorithm. Yes, memory. That's what, no? Processing CPUs. The larger the CPU, the memory size will also increase, right? So it requires computing power. Otherwise, random forest is known to have better accuracy than your decision tree models. And random forest works very well on large scale data sets. One thing is you need to give computing power. As long as the memory is there, it will do its best job. It's very easy to implement. It works with missing values. It works with outliers. It works with what you call any type of data, categorical, numerical, all types of data it works. And it is both a classification method as well as a regression method. You can use it for both regression as well as for classification. The only problem is computing power.
For example, there are multiple levels.
What do you mean by multiple levels?
For example, you are rating it on a scale of 1 to 5. So can you do majority of
No, that's completely different. You are taking the concept in a wrong way. It is tree-based predictions, and the predictions will be voted. No rating skills, nothing here. It will take the what is the observation prediction in tree number, where how many trees it come, and what is its majority prediction. That's all.
Why value? If it has multiple levels, does it work?
Yeah, any type of data, multinomial, more than 2 levels, 10 levels, 100 levels, 200 levels, 1,000 levels, it will work. But only thing is computing power. If you give it the algorithm computing power, it has one of the best performance in the data sets. But it requires computation. Amazon, Google, they use this algorithm day in and day out for various processes. And there they predict multiple, more than 2. Google uses this in their image searching, image processing algorithms. And in images, there will be hundreds, thousands, right, to be predicted. So it will be used here. So this is a very powerful algorithm, requires only the computing power. So random forest was initially created to overcome the problem of overfitting in decision tree. Okay, so we'll take a break. So decision tree, random forest. Giving it up.
When you decision tree
Large scale data sets, this will has very good performance. On small data sets, it does not perform well. Random forest does not perform well on smaller data sets. It performs well on large scale data sets. So I've sent the notebook, you can look at it. You can take your break. So random forest bootstrap sampling So there is one method of bootstrap sampling. You can see here, bootstrap one, you have observations, X8, variables X8, X6, X2, X9, X8, X1, X4, X8. These are observations, not variables. You can see here. Bootstrap sample 2, bootstrap sample 3. And from the same sample, it also creates the test data set. So this is called bootstrap sampling. And then data with replacement.
They take samples for different data and they create decision trees and they create tests on the same samples and
Predict it also.
for each decision tree.
See, this is a data with replacement method. So C1 is appearing in this sample, 2 samples, and then further samples also will appear. You see here A2 is appearing here and A2 is appearing there. B2, so B2, so these are the different types of, this is the original data set. From this, you create the bootstrap samples. Randomly selected observations and randomly selected variables. And then for every sample, one decision tree is built, and then the aggregation will be done for the output, and then the majority decision will be taken. One sample, one decision tree. So 1,000 samples, 1,000 decisions. Data with replacement method. Now, let us continue with the theory only, the opposite model, tree-based models, multi-tree models, ensemble methods. The second method is boosting. The popular algorithm, gradient boosting machines, also called as GBM. Tree-based models, multi-tree models, ensemble methods, boosting is the next type of method. Popular algorithm is gradient boosting machines. Now, GBM is developed to work particularly on weak learners or wrong predictions. The reason why boosting algorithms were developed was to reduce the error or to make the weak learners or wrong predictors learn correctly. Gradient boosting machines, GBMs, are developed to work to boost the weak learners. Step 1, specify the number of trees to be built. which is n underscore estimators is equal to 1000. First, to specify the number of decision trees to build, n underscore estimators is equal to 1000. Step 2, create sample 1, which is randomly selected 65% of rows and square root of number of columns. So create sample 1, which is randomly selected 65% of rows and square root of number of columns. Step 3, build decision tree for sample 1 and also predict. Step 4, identify the wrong predictions and move them to sample 2. Step 5, replenish sample 2 with more data. Step 6, build decision tree 2 for sample 2 and predict. Step 7, identify wrong predictions and move them to sample 3 and continue. Continue this process. Sequential building of trees. Random forest, parallel building of trees, because each sample is independent. Here, sequential building of trees, because each tree is dependent on previous tree for sample. Until tree 1 is completed, until it is predicted, wrong predictions are observed, sample 2 cannot be created. Until sample 2 is finalized and then tree 2 is built, wrong predictions identified and move to sample 3, you can't build tree number 3. Sequential building of trees. So, sequential building of decision trees, as each tree is dependent on previous trees per sample. Understood the context of parallelization in random forest and sequentialization. It is sequential trees. Until one tree is built, you cannot go to the second tree. Until tree 2 is built, you can't go to tree 3. Sequential building of trees. And more weightage is given to wrong predictions in the sample. Slight weightage is given. A 10% additional weightage is given to wrong prediction. Weights are added. That means all observations will not be treated as equal. These observations which come from wrong predictions will be given more weightage. That means they will be given more preference in terms of value. A weight is added to their value. That means their values will be slightly enhanced. And observation values will be enhanced. And then they push them into the trees so that it will be rightly predicted. Now, boosting wrong predictions or boosting weak learners through multiple trees will increase the prediction levels, increasing the decrease the prediction error. Will decrease the prediction error to some extent. To some extent, it will not completely eliminate the error. It will reduce it to certain extent. So GBMs have certain high level performance compared to random forest. GBMs have slightly or marginally higher accuracy compared to random forest. Random forest has a marginal higher accuracy than decision tree. Decision trees slightly perform better than the base models like multiple linear regression and logistic regression. The problem with our Kaggle data is it's a small data. On small data, tree-based algorithms don't perform well. At least minimum data size should be more than 10,000 observations. The larger the data size, the better is the tree-based algorithms performance. So why we are not meeting that assumption of slight improvement compared to the base model is in Kaggle house price prediction is sample size problem. We have only 1469 and we have 80 variables. Typically, how many we need? 80 into 20, 1600, right? 80 into 20, we need 1600 observations. 80 variables are there, we should have got 1600 observations. But we have only 1450 observations. So the sample size is getting us problem here, where the accuracy levels are better for base algorithms compared to the advanced algorithms. These are all advanced algorithms. And these are all CART techniques. CART techniques means they can be used for both classification and regression. CART, C-A-R-T, classification and regression techniques. Tree-based models are CART techniques. That means they work both on classification and regression techniques. Tree-based models also work as unsupervised learning models because they give feature importance or variable importance as part of their output. As part of their output, they give variable importance. So they can also be used in unsupervised learning data. Tree-based algorithms work with outliers. Even if the outliers are there, they have a good performance. Tree-based algorithms work with missing values. They can impute missing values. They can be used for imputing missing values. We'll go work on missing value algorithms. Mice algorithm. That means multivariate imputation using chained equations. There we can choose method as decision tree, method as random forest. That means it uses a random forest algorithm to impute the missing values. There's an algorithm called misforest. Misforest is an algorithm that uses random forest to impute missing values. Algorithm and manual. Till now, we have used only manual techniques. Manual techniques means we'll take the same column values and we are imputing it. We are not taking the other columns or other variables impact on this data, which algorithms will do. Algorithms of missing values will take the impact of other independent variables on the missing values, and then accordingly they will impute. So we will work on missing value algorithms. There are popular missing value algorithm called the mice. Multivariate imputation. It simultaneously imputes numerical data and non-numerical data. The method is predictive mean matching, random forest, neural networks, decision tree. All these are used for missing value treatment. So these are very powerful algorithms. These are very interesting algorithms in terms of accuracy. They are very easy to run. They are very easy to understand. They are very easy to implement. They work on large scale data. Regression does not work more than 1 lakh observations are there. Your regression will not work properly. Whereas these set of algorithms, they work very, very well on large scale. Only thing they need is computing power. They need computing power. If you give them computing power, they process the data and they work really well. So sequential building of decision trees is very important in boosting machines. So this is a classic example of boosting algorithm. So full image is not coming out. One second. The full image. They didn't put full image itself. See? So this is your original data set. We classify it. Then weight is increased to the wrong prediction. See, these blues are wrongly predicted. You can see here, right? This is red, this is blue. These are wrong predictions. These two observations are predicted wrongly as blue. This prediction is predicted wrongly as red. So in the next iteration, it gives weightages to these wrong predictions. And then they'll pass them through the model again. Now it draws a line. Now you can see here the red book has come to the right level, but blues are still on the wrong predictions. So now in the second iteration, it increases the weightage for blues and then builds the model. And then here red again comes back to the thing. So it goes through this process. Identifies the wrong predictions, gives more weightages, passes them to the next tree model, and hopes it gets predicted correctly. If not, again it will be pushed into the model. And whenever it goes into the model, weightages are given to those things. You can see the size of the dots increasing, right? So weightages are given to this wrong prediction.
Every time example data will be added to the new tree.
Which one? Yeah, along with the wrongly classified data, some data is taken from the data universe also. Some amount of data is taken from the data universe also.
That's only the final prediction.
No. Here, what happens is, for the right predictions again will repeat. Now here also right predictions will repeat along with the wrong predictions in some samples. Again, majority voting methods and regression, same thing. For final prediction, it is majority voting and what you call regression only. Average method for regression. So here also majority voting for classification and average method for regression. See, in random forest also you get wrong predictions, right? Here also you get wrong predictions. And then slowly it will be pushed towards the right predictions. The domination of right predictions will happen over a period of time. Then there are these wrongly predicted values might get pushed towards the majority correct predictions. Might get, not I am telling you, because 100% you cannot correctly in real-time data sets. See, textbook data sets like IIDs, diabetes, you can do all those things there. But when you're looking at real-time data, it is not at all possible. See, Kaggle, how much we went through? Kaggle is a real-time data. Zillow, it's a housing price company, like Magic Bricks we have in India, right? Zillow is the company which was established 30 years back during that dot-com boom. That was the first company to sell online research, second-hand houses online. Second-hand houses were sold online by this company called Zillow. They developed the software, and then people thought, you can't sell a house online. But now you can see, right? Magic Bricks, 99 acres, a lot of things are there, right? Where you can do house-related transactions online. So same thing here. Zillow was the parent company, the pioneer in predicting the second-hand house price. This Kaggle data is given by Zillow in a competition some 20 years back. Same data, still fine-tuning is required. Still people want to compete on the data, working on the data again and again to improve it. Okay, so these algorithms will always have certain amount of error because there is always some uncertainty in an event. See, look at the Ukraine war. Joe Biden was telling 1 month before saying that the war will happen. But the Indian Prime Minister did not believe that war will happen. Otherwise, 1 month back only, he could have brought the students back from Ukraine to India without any problem. The problem which happened was failure of Indian government to believe that war will happen. Uncertainty. American president, see, you cannot see American president, whatever he talks, he has to be very, very careful. He can't speak a lie. If he speaks a lie, he will be impeached. Like what happened with Trump. So American president cannot speak something which is not 100% true. When Joe Biden was saying Russia is going to attack Ukraine, that to 30 days in advance they were telling, and he was supported by the French president and German president, Indian Prime Minister did not believe. Of course, he has his own reasoning. Uncertainty. He has some uncertainty. He was thinking, no, this is some threatening going on. What will happen? But those guys know with 100 because they have their inside men. Americans have intelligence people within Russian intelligence. French people have intelligence within Russian intelligence. India does not have it. Had India also had intelligence within the Russian intelligence, maybe he would have got convinced and moved all his people 1 month back. That uncertainty will always be there. No matter how confirmed you are, people will not be 100% sure. Same thing happens here in statistics. There will be certain factors which might not have emerged. See, I have seen a research report on December 29th last year that oil price will touch $100 per barrel in the month of November 2020. This report is given by Goldman Sachs. Goldman Sachs is known to be the best investment firm in the world. Now, what happened to $100 barrel? It came in last week of February. Now it is going towards $180. If the war continues for another 10 days, barrel will become $180 and our liter petrol will become 160 rupees per 1 liter. Because of UP elections, they are not increasing the price, right? At one go, they will increase 10 rupees every day, 160 or 170 rupees per liter is going to be your petrol. CNG, your LPG cylinder, which is being at 1,200 rupees now, will go to 2,400 rupees. Because LPG is mostly supplied by Russia. Simple. So uncertainty is there. So nothing is 100%. Same thing we have to assume in machine learning models. We should not target for 100%. In reality, we just look at 70 to 90%. If our models give us a 80 to 90% accuracy, we'll be very, very happy. You will see as we go through large scale data sets like Black Friday sales. We have not worked on Black Friday sales, right? That is 5 lakh observations. Including test data, it has 8 lakh observations. Their regression will give you horrible. He has already run it, right? R square is not even 10 per 0.10. For that data, decision tree will give you R square of 52. Random forest will give you 70. So like that, it will happen. Neural networks and deep learning will give you above 85. So that sort of uncertainty will be there. So gradient boosting machines will try their best to boost the weak learners, but there is no guarantee that the weak learners will become right. As the image shows, even after doing so much thing, the red is still classified as wrong. See, no matter how much you rotate the axis, do these things, the red is still kept as error. Error has to be there. So this is what happens with boosting algorithms. They try their best. And if you are looking at bagging, boosting, what their whole difference is, this is the difference between bagging algorithms and boosting algorithms. See here, Bagging is parallel because each sample is independent. Until sample is done, pre-process will not start. In random forest, until sampling is done, the tree building will not start. Here what happens? Sample 1, tree 1, and tree 1 to sample 2. The blackbirds are wrong prediction. Sample 2, then tree 2, then from tree 2 to sample 3, again tree, sequential. Until one tree is completed, you cannot go to the next. Each tree is dependent on previously for sample. Yeah.
So, like, where do they get the test data?
Within the same data. Same data we use as train as well as same data you use as test. Same. Mostly also same process will be there. Or 65-35.
What about time frame?
Which one?
When you compare to
See, GBM is light on memory. Light on memory. It does not require that large scale memory which RF requires, random forest requires. But time consuming is high in GBM. Random forest memory is required and what you call time is less. In terms of memory requirement, random forest requires large computing, but time is very small. Whereas in sequential modeling, less memory, more time, because it's a sequential process, right? Slightly more time or little bit more time than your random forest, but processing less in sequential. Whereas processing is high in random. Suppose you are dealing with 4 GB. Data is 4 GB. Thousands, if you are creating 1,000 samples, 4 GB will become 8 GB, right? Not if 8 GB, 6 GB. 6 GB is a very large data. Now memory space will not be there for 6 GB to process in a 4 GB RAM or 8 GB RAM. It will say memory size is not enough. For sample storage, there is no memory space. In sequential, we don't get that problem. Small sample for 4 GB, it will take say 400 MB sample size, build the tree, send to the model. Now the final model, by all this model output will be equal to 4 GB. 400, 400, 400, it will add and becomes a bigger tree. Here, random forest, it initially requires a larger sample and then it breaks down into trees into smaller trees. So it's opposite to it. So boosting and bagging are opposite processes, but both of them have better accuracy compared to the base models on large data sets, not on small data sets. When I say large, I'm talking about observations greater than 10,000. Greater than 10,000 observations we consider as large data. But in big data, it will be, some people say million rows is a lot of big data. Some people say, 1 lakh rows itself with 100 variables is a big data. Some people quantify big data in size, 1 GB data, 2 GB data, or 5 GB data. So that all different definitions are there. But let us go with the number of observations in the early stages. Later, when we go to large scale images, like he was asking the Apple thing, the Apple shelf life, the data size is around 2 GB. That's why it has to be run on Kaggle only. The shelf life, no? Apple, carrots, banana, everything is there. Not one fruit. It's not one fruit. That internship data we got now. Fruit and vegetable data set, Kaggle. You want, you can try it. There is some sample code also available. Data set is 179 MB. So images are of apple, banana, carrot, tomato, and again carrot. Apple, banana, tomato, and carrot. 2 fruits and 2 vegetables. These are the various images of apple, and these are the images of expired. Expired means which are gone bad. So these are bananas, this is apple expired. You can see the fruits, right? So this type of, when you have this type of data, I would suggest if you want, you can, we have not got image processing, right? So when we have image processing, I'll try to do this data set. Okay. But we'll go even more advanced, like X-rays, ultrasound scans. We'll look at 100 prediction images, CFR 100. Where you'll be looking at whether the image is a shed, a horse, a train, bus, scooter, 100 categories in it. So that sort of images are also there. So you can see there is some code available here. If you are interested, I think only one guy did, same guy has uploaded the data, and he also did it for the same thing. He has run a, I think, convolution neural network, CNN. Yeah, CNN he has run. Convolution neural network he has run with how many weights? 1,79 lakh, 4, not 1 crore, 17 crore. 17 crore, 94 lakhs, 57,475 weights. So it's a very large scale model, which has to be run on GPU. You can run it on CPU, not on our laptop. We have to use Google Collaboratory or Kaggle. Kaggle provides GPUs. So either it has to be run on Kaggle or Google Collaboratory. We will run deep learning on Colab only, and one model on Kaggle. So that will be part of your, once all the algorithms are done, then we do time series, then we do NLP, then comes your deep learning. Okay? So there is still time. So I would suggest a better way rather than going for that internship. All right, all of you understood the context of boosting and bagging? Yeah. Now, how do we decide number of trees? It again trial and error. There is no fixed formula to decide the number of trees. We'll go, actually in R, we have the plot. Once you build the trees model, you can plot the tree and see where the line is becoming a straight line. That means the variance is becoming 0 or stagnant, constant. So you will look at the edge or the bend point where it is there, that will be your number of trees. So in Python, generally RF and GPM we build in R and then come up with the number of trees, and then we use it as a required thing in Python. Otherwise, Python also can plot the variance of trees and then we can find the value, but requires a little bit of code writing in that. Elbow plot, or it's not basically elbow plot. It's a variance plot where it becomes a straight line. It does not look like an elbow. Elbow tree plots we use in clusters, where the image looks like an elbow. Here it is like a straight line. The point you'll have slight up and downs, but after some point it becomes a dead line. So that means there is no change. So we'll go to the point where the change happened. That will be our final number of trees. So from sklearn dot ensemble import random forest regressor. Because we are running it as a regression algorithm, we'll take it as regressor. RF is equal to random forest regressor n underscore estimator is equal to 1000. RF model is equal to RF dot fit x comma y. So RF model dot score x comma y 98.30. RF predict is equal to RF model dot predict house test here. PD dot data frame RF predict dot to underscore CSV RF dot CSV. You submitted. You got how much you got? 1,400. That's slightly greater, right? Then make it 3,000. Make it 3,000 estimated and then do it.
Regulation
3,000 trees. If you try 3,000 trees, ఎంత తగ్గింది? So that means random forest is 3,000 trees is not causing change. That means you can go with 1,000 trees only. 1,000 is okay then. That means it's not causing much of change. Waste of computing power. All right, all of you have run the random forest regressor. It ran. So from sklearn dot ensemble import gradient boosting regressor. From sklearn dot ensemble import gradient boosting regressor. GBM is equal to gradient boosting regressor n underscore estimators is equal to 3,000. Let's see. It's not overfitting color. That is not a marginal. That is marginal changes. Overfitting means you should have 20% difference. 20.
Cross validation చేస్తుంటే సార్
74% వస్తుంది.
అది అటు చూసుకున్నా 4% లేకపోతే 7%.
ఎక్కువ. It will be 20%. Check. Maybe this is a small data, you might get it like that. But on large scale data, it will be a different story altogether. GBM model dot score x comma y 99.99. GBM predict equal to GBM model dot predict house test here. Data frame GBM predict dot to underscore CSV GBM dot CSV. Inta 1.3. Linear kalla is better. 1.3. Try with 5,000. I think it should go to 1.340 or something. 5,000. So you have to understand the hierarchy of models, right? Base models, tree models, ensemble methods. Then we'll split. Some models are exclusive for classification, like NABIS is an exclusive classification model. KNN also can be used for both regression classification, but predominantly it works for classification only. Then support vector both works as regression classification, but predominantly in classification. We'll study those algorithms. Next set of algorithms will be these. Next, we will study support vector regression and classification and KNN. KNN regression and KNN classification. And these are manually calculating is impossible. That's why I'm not showing them in Excel. But these two algorithms manually calculating is difficult. But they use the same Gini and entropy calculation, same. In a day you can serve with only 10. Max is 10. Okay. Now, if you want to upload this in GitHub, you have not uploaded in GitHub, right? Or you have uploaded? We have this something called So if you can open this pull request, okay, no pull request, new repository or import repository. No. New repository name is house price prediction. Public, create repository. Okay. Once you create repository, you first download this IPNB file. Download as IPNB file. Then go to your repository. Here you see here, create a new file or upload an existing file. Upload an existing file, choose files. It's downloading. Yeah. This is 1728. Yeah. Click open. Okay, it has this, and then commit changes. And this is my file. So the theory, everything is here. You can see here with outputs. All will be same IPNB file will be uploaded. Your outputs, your things, everything is. So you just need to upload the IPNB file directly. But make sure you write your exploratory data analysis must be there. At least 2 or 3 hypothesis tests, some pie diagrams, bar charts of some variables like that. You have to do at least 5 to 10 EDA, and then 2 or 3 hypothesis tests, and then model building and comparison. Right? You can add a little bit of EDA to this notebook and you can upload it. And it will be there. You can put up your GitHub profile link, GitHub link directly. And then you can add it to your resume. Okay. So you have to start working on your GitHub profiles also right now, because we are doing multiple models right now, right? We are in the advanced models. So as and when required, you can delete the old file and you can upload the new file also. As we add models to the theory, we will have one comprehensive project with all models, like house price regression. Okay, we will do what you call support vector regression, KNN regression on the data. Whether right or wrong, we will implement to understand the algorithm. We will do neural networks on the data. And then we will also build a deep learning model on that data. And deep learning model means many layers model. Then your choice, HR analytics is there. HR analytics also will implement all these models. Not only will implement HR analytics, you can implement classifier, right? The other data we have, HR analytics. So on that, you can implement decision tree classifier, random forest classifier, and GPT classifier. Or in the next session, first we will do that. Okay. And then